So, in the last class I have solved one problem on pile in homogeneous sand, and then I calculated the load carrying capacity of the pile without considering the critical length concept. Okay. I consider the total effective overburden pressure at the tip as well as the along the length of the pile. Now, the same problem I will consider, and then I will introduce the critical length concept in that problem, and then I will calculate the new load carrying capacity of the pile. So, this is the problem, and so the here I will take this example part B, and then here I will introduce the critical length concept. Similar way we can introduce these things on part A also, but I will do on the part B only. So, last class in the part B, without considering critical length concept, the loading was 1133 kilonewton. And so, now here I will consider the So, if I consider the critical length, then what will happen, that the same, this is the ground surface, this is the water table position, and water table position is 2 meter, and this is the pile is 15 meter. So, this is 2 meter, this is 0 meter, and this is 15 meter minus 15 meter, where the pile is resting. But here the phi value is 40 degree, same as the previous case. NQ value is also 130, and K value is 2, and delta is 0.75 of phi. So, that is 40 degree 30 degree, and D value is 0.3 meter, and length of the pile L is 15 meter. So, all the data are same. So, now as I am considering the critical length concept, so first let us see. So, what is the critical length of this type of problem? So, the critical length, if you see that last to last class note, then you will find that critical length by D is equal to 15 for loose to medium sand, and critical length by D is taken 20 for dense sand. So, here the phi value is 40 degree. So, it is in dense sand. So, we will consider that our critical depth is 20 times of D. So, it is 20 into D is 0.3. So, it is 6 meter. Okay. So, the critical length is 6 meter from the ground surface. So, the distribution is up to 2 meter. Again this value will be 38 kilonewton per meter square, because that is the value that I got in the last class. Okay. Now, in the up to 6 meter, so this is up to 2 meter minus 2, this is 0 meter, this is 6 meter. So, up to 6 meter, this value is 38 plus 4, this difference is 4 meter into 19 minus 10. So, that value is 74 kilonewton per meter square. So, this is 74 kilonewton per meter square, and then up to 15 meter from the 6 meter, the stress will not change. Okay. So, that will remain same, because that is the concept of critical length theory. So, that means here also this is 74 kilonewton per meter square. So, now at the tip also we are considering 74 kilonewton per meter square. So, my Q P U is equal to sigma bar N Q, and sigma bar is here at the tip 74, N Q is 130. So, this value is equal to 9620 kilonewton per meter square. So, as I mentioned in the last class that this value is less than 11,000 kilonewton per meter square, but some researchers are considering or suggested that if this is this value is greater than 11,000 kilonewton per meter square. So, you can take it 11,000 kilonewton per meter square, but I would consider the value actual value that is coming from the calculation, because that is the value, and few researchers have suggested that you take the total values that is coming. So, that is why I will concentrate on the total value, whether it is a considering critical length or not. I will consider the total values that is coming. So, here it is 9620. Okay. So, and even if it is greater than 11,000 kilonewton per meter square, but I will still consider that higher value, because that method I prefer to consider. So, and then I will find that F s, this is the or Q P U is equal to, again this is 9620 and area is this 0.071. So, that will be equal to 683 kilonewton. Okay. So, that is considering the critical length concept. Now, the friction part F s 1, that is from 0 to 2 meter. So, again if you look at this diagram, so this will be the average value will be 0 plus 38 into 2 k is 2 and tan 30 degree. So, this is equal to 22 kilonewton per meter square, and F s 2, that is 2 meter to 6 meter. Okay, this one. So, this will be again average, here it is 38 and here it is 74, then 2 k value is 2 and tan 30 degree. So, that is equal to 65 kilonewton per meter square. Then F s 3, which is 6 meter to 15 meter. So, that is equal to, because there is the uniform pressure. So, this pressure is uniform. So, I will consider only 74, then k value is 2 and this is tan 30 degree. So, that is equal to 85.5 kilonewton per meter square. So, the total frictional force is equal to pi into d is 0.3. Then first part F s 1 is 22 and the length is 2 meter. This is the length is 2 meter, F s 1 is 0 to 2 meter. So, 2, then F s 2 is 65, length is 4 minus 2 or 6 minus 2, this is the length, plus this is equal to 85.5 and the length is 15 minus 6. So, that will be equal to 1011 kilonewton. Okay. So, this is 6 minus 2 and this is 15 minus 6. So, my total Q is equal to 683 plus 1011, that is equal to 1694 kilonewton, and so Q safe is equal to 1694 divided by 2.5. So, that is equal to 678 kilonewton. So, if you look at the previous problem, so this is 1133 is without considering the critical length, and which is further reduced, and it is 678 kilonewton if I consider the critical length concept. Okay. In the same method, we have done considering full effective overburden pressure, one problem, and another problem we have done considering critical length concept. So, now both the methods people are using. So, now one thing, it is the designer's decision which one they will choose, but I will show you both the methods, and then in layered soil also how we will take care the problems considering critical length and without considering the critical length. Okay. So, the next problem, the same problem I will solve by using the Meyerhoff's method. Okay. So, the same problem I will solve considering the Meyerhoff method. This is the Meyerhoff methods, and here also Meyerhoff methods as suggested you have to consider critical length. Okay. So, that means the critical length concept we will use in the Meyerhoff method, and then also in the limiting value of bearing capacity also we will consider. Okay. And here in the chart you see that in the chart it is 40 degree, and the value of NQ that we are getting is here. So, that value we are getting is, this is the NQ curve, and this value is here. So, this value is around NQ is equal to 320. Okay. So, the NQ value is 320 as per Meyerhoff method, and you can see the Meyerhoff method, this is the critical length concept is used. So, and they have suggested some limiting tip resistance also for the dense soil. So, our case it is the dense soil, we will consider this limiting tip resistance concept, and the NQ value corresponding to 40 degree phi is 320. So, the same problem if I solve with Meyerhoff methods. So, by using the Meyerhoff theory, so you will calculate that the same phi equal to 40 degree, NQ value is coming out to be 320, then our K value again we are taking 2, and delta value is 0.755, that is 30 degree, and we are using the critical length concept. Okay. So, this is the same water table is here, then 6 meter, then it is uniform. Okay. So, this is 74 kilonewton per meter square, and this value is 38 kilonewton per meter square, and this is also 74 kilonewton per meter square, and this is minus 6 meter, this is minus 2 meter, and this is minus 15 meter. So, these are the total stress distribution. So, the your QPU is equal to sigma bar into NQ. Sigma bar is 74, that is at the base, and then it is 320. So, that value is equal to 23680 kilonewton per meter square. Now, Meyerhoff suggested that QPU limit, there is a limiting value, and for the dense sand that limiting value is 50 NQ into tan phi. Okay. So, that means your QPU should not be greater than QPU limit. So, that is 50 into NQ is 320 and tan 40 degree. Okay. So, that value is coming out to be 13425.6, that is kilonewton per meter square. So, this is the limit and your value is 2 3. So, it is greater. So, we cannot consider this value. So, you have to consider this value. So, that is why your QPU limit is greater than equal to QPU, or in other word you can say that QPU cannot be greater than QPU limit. Okay. So, this cannot be greater than QPU limit. So, that is why we have to consider our QPU is equal to 13425.6 kilonewton per meter square. So, my QPU, the area is same 13425.6 into 0.071. Okay. So, that is equal to 953 kilonewton. And but the friction resistance part will remain same, because we have not changed the friction resistance part. So, that is the same value that we have considered last time. So, that is 1011 kilonewton. So, the Q ultimate is 953 plus 1011, that is equal to 1964 kilonewton. So, Q safe is equal to 1964 divided by 2.5, that is equal to 785.6 kilonewton. Okay. So, my previous problem, this value was 678 kilonewton without considering critical depth using the first method, and now with considering the this is with considering the critical depth, by using the first method, and now by using the Meyerhoff's method considering the critical depth or critical length. So, that we remember that when you are using the Meyerhoff methods, you have to consider the critical length concept. Okay. So, that is 785.6 kilonewton. Now, the same problem I will do with considering the IS code. Okay. So, let us see how I can do it. So, now this is the Meyerhoff's method I have discussed, this is the limiting value, and these are the values I have taken. Now, I will go to the IS code part. So, it is a homogeneous soil, it is for the layered soil also, but it is the homogeneous case. So, here I will go for the IS code part. So, difference is that here that it is a driven pile. So, the and 40 degrees. So, I will take k value is 2 as recommended by the IS code. So, it is 2 I will take for the 40 degree, and then the and then for n gamma value, because IS code we have to consider the n gamma corresponding to 40 is 109.41, that is the n gamma corresponding to 40, and the NQ value, and here the NQ value is, you have to consider NQ value here. NQ value corresponding to, so this is the driven precast or cast in situ concrete pile. So, this is the driven pile. So, for the driven pile you have to use this chart, for board pile you have to use this chart. So, for the driven pile corresponding to phi 40 degree. So, this is the value. So, that value is coming out to be again 130. So, NQ is equal to 130. Okay. So, now I will use the IS code method. So, if you so, this is the IS code method, and area of the base half into diameter into gamma into NQ, okay, N gamma plus PD into NQ. PD is the effective overburden pressure at the tip of the pile. So, now if I write the IS code method, if I consider the IS code method, the same problem, if I consider the IS code, now my NQ value is coming out to be 130, K I am taking is 2, but IS code recommended that you take delta is equal to phi, because when I mention about the IS code, I mentioned that they have recommended the delta may be taken as a phi. So, I have also taken delta is equal to phi is 40 degree for the concrete pile. Okay. And another thing is that about the IS code has mentioned that if your length of the pile is more than 15 d to 20 d, then you consider the effective overburden pressure corresponding to 15 d to 20 d case, which is similar to the critical depth concept. So, for the IS code also you have to consider the critical depth concept, because as by my understanding that from 15 to 20 d's part the stress will not change. So, in that case, so as per the IS code, here it is dense soil. So, they have mentioned for 30 degree so I mean loose sand it is 15 d and dense sand it is 20 d. So, here it is dense sand. So, we are considering critical L critical to D is 20. So, that means L critical is again 6 meter. So, the same things we will use, this is up to 2, then 6, then it will uniform. Okay. So, this will be the 74 kilonewton per meter square, this is the 6 meter, this is the 2 meter, minus 2 meter, minus 6 meter, minus 15 meter. So, this is 38 kilonewton per meter square, and this is the value which is 74 kilonewton per meter square. Okay. But in IS code NQ part is also there, N gamma part, NQ is 130, N gamma part is also there, N gamma is 109.41, that from the table that I have shown. Okay. So, now let us start. So, we will start Q P U, that is equal to half into D into the N gamma into gamma. Gamma is the unit weight of the pile, and then plus that sigma bar into NQ. Okay. So, if I put this value half into diameter of the pile is 3 meter 0.3 meter, NQ is 109.41 into gamma is 19 kilonewton per meter. Okay. So, this gamma is consider 19 kilonewton per meter minus 10, because it is under the submerged condition. So, then plus n bar is 70 q, sigma bar is 74 into 130. Okay. So, this will be the for the QPU, and the friction part Fs 1 0 to 2 meter is equal to the same average into 0 plus 38, k is equal to 2, but tan delta will be tan 40. Okay. So, that is equal to 32 kilonewton per meter square. Similarly, Fs 2 meter to 6 meter, that is equal to the same, only difference is tan delta will be the tan 40, that is 38 plus 74 into 2 into tan 40 degree. So, that is equal to 94 kilonewton per meter square, and Fs 3, that is 6 meter to 15 meter. So, that is equal to half, sorry, because it is uniform. So, this half is not required. So, that will be equal to 74 into 2 into tan 40 degree. So, that is equal to 124 kilonewton per meter square. So, my Q s is equal to 0.pi d into 32 into 2 meter plus 94 into 4 meter plus 124 into 9 meter. So, that is equal to 1466 kilonewton. Okay. So, finally, we have to add these two value and Q P U, that A B into Q P U. So, A B is 0.071 into Q P U. So, finally, you add these two, then you will get the Q P U plus Q S, and the Q safe is equal to Q U divided by 2.5. So, you add this two and you will get the value of safe load carrying capacity based on the IS code. So, in summary, I have discussed three methods. So, first methods I have discussed considering the full effective overburden pressure, that means without considering the critical length concept as well as considering the critical length concept. Okay. And in the second method, I have discussed the Meyerhoff's method, where the critical length concept is used, and in the IS code method also critical length concept is used, because IS code is recommended that you cannot take the effective overburden pressure more than corresponding to the effective overburden pressure at 15 to 20 D depending upon the type of soil. So, in the three methods, so we have discussed. So, and one more thing, in the first method, that in the second method, Meyerhoff's method, there is a limiting tip resistance value is given. So, we have checked that condition. IS method is not suggested in that kind of check, but in the first method, as they has suggested that here you can consider a limiting value of tip resistance, that 11,000 kilonewton per meter square, and in the friction resistance also you can limit with 100 kilonewton per meter square. But I would prefer to consider that total stress or the load that is coming considering the full effective overburden pressure as well as the critical length concept. So, and here the question is that I have solved the problems by considering critical length and without considering critical length. Now, both the methods people use, and now you have to judge your own judgment, and then you will decide which one you will consider. Okay. So, in the next class I will discuss about the bearing capacity of pile in layered soil, how we will calculate the bearing capacity if it is in the layered soil, sand, and then later on we will discuss about the clay and then sand clay both. Thank you.